Okay, so a scientist noticed an oil slick that is floating on water. So here we have air, here we have oil, and here we have water. And then somewhere up here we have a scientist, and she's looking down. And the way it goes, she's looking at the reflection off of some part of the surface. So if I look at, for example, it might be reflected sunlight. Here's the sun up here, and there's light coming down, and it's actually at normal incidence, but some of it will be reflected off the surface of the oil, some of it will transmit into the oil, and then reflect off the surface of the water. Maybe even some more of it will actually go down into the water. But the point is that she's seeing this reflection if there's constructive interference between beam 1, the first reflection, and beam 2, the second reflection. And I've drawn this at an angle to make it easy to draw, but in fact, for normal incidence, here normal, meaning that they're going straight down into the water, incidence, then 2 travels delta x equals 2 times t further than 1. Okay. So that's the basic idea. And they give you various things, all these indices of refractions, and they're asking you for find minimum thickness. So find minimum value of t, for constructive interference. That's something that's not really said there. But when you have constructive interference between beams 1 and 2, then you will see a lot of energy reflected. So I'm going to use equation 21.30 from Knight, 21.30, which you can go and look up if you'd like. And what it looks like is that delta phi is equal to 2 pi times delta x divided by lambda f, which is actually the index or the wavelength of light inside the film, plus delta phi sub 0. And the way it works, I'll scroll down a little bit here, is that if you're going from an index of refraction that's less to an index of refraction that's more, then delta phi from going from the 0 to the 1 is going to be pi. Every time you reflect off an index where the next medium, the wave's traveling slower, the reflected pulse is inverted, okay, or upside down. And so for a sine wave, that amounts to a difference of pi. And then the second interface, n2, is also greater than n1, and so this means that the delta phi from 1 to 2 is also pi. And so this delta phi 0 is going to be pi minus pi equals 0. And so there's no phase difference there, but you want constructive interference, which will be delta phi is equal to some integer times 2 pi. And so we can solve that out by saying that delta phi is equal to 2 pi times 2t, that's your delta x, divided by lambda in the air divided by n1 in the oil slick, okay, equals m times 2 pi. And then solving that out for a little bit more, we would see that 4 pi times n1 times t divided by lambda out in air is equal to m times 2 pi. And the minimum t occurs, and that is non-zero, I guess, not non-zero, is for m equals 1. So if you put in m equals 0, you get thickness equals 0. If you put m equals 1, or 2 or 3, you'll get higher and higher thicknesses. So the thinnest one is t equals just lambda sub 0 divided by 2 times n1. That's 750 nanometers divided by 2 times 1.2. And that's equal to 313 nanometers. Okay, part B says suppose the oil had an index of refraction of 1.50. What would be the minimum thickness T now? So now what you've got is that N1 is still greater than N sub 0, so that means that the delta phi from the air into the oil is still pi, but N2 now is less than N1. So what that means is that the delta phi going from the oil into the water now, since the oil is the thicker medium, when you reflect off a medium which has a lower index of refraction or a faster medium, this is called internal reflection, and there's no phase shift. It will come back the same way up. So now delta phi sub 0 is equal to pi minus 0, which is equal to pi. And so now delta phi has a different equation. It's going to be same 2 pi times delta x, which is still 2t, divided by the lambda film, so that's lambda in the air divided by n1. But now it's plus pi. And so again, if she wants to see the light, you use constructive, so that delta phi is equal to m times 2 pi, so delta phi equals some integer times 2 pi. And then let's just write that out. So 4 times pi times n1 times thickness divided by lambda sub 0, okay, plus pi is equal to m times 2 times pi. And we can try to sort of solve that out. We end up with this 4 pi n1t divided by lambda sub 0 is equal to 2 pi m minus pi. And again, the minimum of t that is non-zero is, I think it's going to be for m equals 1 there. If you put in m equals 0, you get a negative thickness. And so m equals 1, you get 2 pi minus pi, you just get pi. And so then you've got equals pi. I'll solve that out for thickness, and I get the thickness is equal to lambda now over 4 times n1. And that's 750 nanometers divided by 4 times 1.5 now is the index for the oil, and that's 125 nanometers. So part C for this question is now saying, assume the oil had a thickness of 200 nanometers, index refraction of 1.5, a diver swimming underneath the oil slick looking at the same spot as the scientist. And it's asking, what is the longest wavelength of light in water that is transmitted most easily? So if we have the reflection is constructive, then that means that you have minimum transmittance. Okay. But if you have the reflection destructive, then that is maximum is transmitted. It's sort of a conservation of energy concept. You have this little slick. If it's reflecting a lot of light, that means it's not transmitting very much. But if it's not reflecting very much, where does that energy go? It gets transmitted down into the water. And so you're looking now for destructive interference on the reflection. So back from part B, we had an equation for delta phi, which looked like this. Delta phi is equal to 4 pi times n1 times the thickness divided by lambda in air plus pi. Because again, the oil slick now has a higher index than the water below it. And so destructive interference now, so that we can maximize light for the scuba diver, will have delta phi is equal to m plus a half times 2 pi. So we just sub that in, and we get that 4 times pi times n1 times thickness divided by lambda in the air plus pi equals m plus a half times 2 pi. And solving that all out, dividing by pi's, I get the 4 times n1 times thickness divided by lambda sub 0 is equal to 2, I get 2m plus 1 minus 1, so it's just equal to 2 times m. And once again, I think the minimum well actually let's solve it up for wavelength. Get lambda sub 0 is equal to now 4 times n1 times t over 2m, okay, which is just equal to 2 times n1 times thickness divided by m. And the longest wavelength, which is what you're asked for there, lambda, is for m equals 1. Again, just choose m equals 1. Any greater value of m you'll have shorter wavelength, and you can't divide by 0, so that's not going to work. So let's just choose m equals 1. Lambda sub 0 equals 2 times 1.5, the index of the oil, times the thickness, which they gave you in the question is 200 nanometers, and divided by 1. And so that equals 600 nanometers. Now that is actually the wavelength out in the air. And if you look very carefully at the question, it asks you for what wavelength in the water. So I guess because the scuba diver is down there. So lambda water equals lambda air divided by the n of the water. So that's 600 nanometers divided by 1.33. So that equals 451 nanometers.